In this video, we're going to take the same circuit that we analyzed in the previous circuit, only this time, instead of bypassing the source resistance with a capacitor that in the mid-range frequencies shorted across this resistor and pulled the source to ground, this time we're going to not bypass the resistor such that R sub S will show up in the small signal model over here and effectively lift the source up off of ground. So R sub S here being left in place raises the voltage of the source. The source voltage is no longer zero. And we're going to go through and analyze this small signal, or do the small signal analysis of this circuit using both the T model and then also the hybrid pi model. You'll notice that for completeness, I've drawn in the early effect resistor, little r sub 0. It of course goes from the drain to the source. In the previous example where the source was grounded, R0 ended up being in parallel with R sub D and R sub L, and it was fairly easy to account for R0 as just another parallel resistance here. But now, because the source is not at ground, R0 is not in parallel with R sub D and R sub L, and it makes for it just adds a level of complexity to our analysis that for our purposes right now, we're going to go ahead and neglect R0. We'll neglect it both in the T model and also in down here the hybrid pi model. You'll notice here in the hybrid pi model, the gate is open, showing no current going in. Up here, of course, we just say, even though they're connected so that the voltage there is the gate voltage, no current enters into it. In the hybrid pi model, it actually shows up open there. VGS is the voltage from the gate to the source. And then we have the source resistance. So once again, the source is not tied to ground. It's lifted off of ground by R sub S. And as we had up here, R0 then goes from the drain to the source. And as we mentioned above, we're going to ignore R0 just to make the analysis a little more straightforward. Let's start our analysis with the T model. And as we can see, V out then is the voltage across the parallel of R sub D and R sub L. With R0 out of the circuit, we've got then the current from the current source, G sub M VGS, flowing through those two parallel resistances, where we have then V out is equal to negative G sub M times VGS times the parallel combination of R sub D and R sub L. Now in this model, where we have both the transconductance resistance 1 over G sub M and R sub S, and by ignoring R0, those two resistances are in series with each other. VGS is the voltage across this resistor, and VGS is in fact then a subdivided portion of the voltage here at the gate. Now in this situation where we haven't modeled a source resistance, the voltage at the gate is just V sig. We'll do it in two steps, but first of all, let's just write VGS then is equal to V sub G, the voltage at the gate. Let's make that a lowercase v, lowercase g, times the voltage dividing ratio 1 over G sub M divided by 1 over G sub M plus R sub S. Now we can simplify this compound fraction by multiplying numerator and denominator by G sub M. And when we do so, we get then that VGS is equal to V sub G times 1 over 1 plus G sub M times R sub S. Now with this expression for V sub GS, we can substitute it in here. And also, as we've already noted, V sub G is V sig. We can write then that V out is equal to, V sub G is just V sig, times 1 over 1 plus G sub M times R sub S. So this right here is VGS. Then we still have the negative G sub M and the R sub D in parallel with R sub L. It's an L there. So again, what we did is in this first equation here, that had VGS in it, we've replaced that VGS with this expression of VGS, recognizing that V sub G is just V sig. And so we can then form the total gain, or expression for the total gain G, is equal to V out over V sig which is then equal to, dividing both sides by V sig, we have V out over V sig is equal to, I'm going to put the negative G sub M in front, negative G sub M times 1 over 1 plus G sub M R sub S times R sub D in parallel with R sub L. This term then becomes the expression for the gain in this circuit given R sub S not being bypassed, raising it up. You'll notice that this term right here then factors in. In our previous example, when R sub S was shorted out, we had that the gain in the previous example, let me just write it up here so we can compare it. We had that the gain was equal to negative G sub M times the parallel combination of the output. It was R sub D in parallel with R sub L. And again, in that example, we left R0 in there because it was in parallel with the rest. But let's just compare this. We've got negative G sub M times the effective resistance, or the equivalent resistance of the output, was the gain when the source was grounded. Now, in this example, the source isn't grounded. And so we end up with a derating. This number 1 over 1 plus G sub M R sub S is a number less than 1, such that the gain is going to be less with the source resistor present. Again, with the source resistor not short-circuited out of the small signal model, the gain is going to be smaller than it was when the source was grounded. And that's really the take-home message for this, is that when you don't short out that source resistor, the gain deteriorates by this factor of 1 over 1 plus G sub M times R sub S. Now, let's just show that we get the same results using the hybrid pi model here. Once again, the output, V out, or V out here, is going to equal negative G sub M VGS times the parallel combination of R sub D and R sub L. That step is the same. But now VGS is the voltage across this dependent current source. There's no voltage division or anything like that over here that we were able to do when the T model was present. So to get an expression for VGS in terms of V sig, we're going to notice that V sig, or again VG in this case, is V sig, and it's referenced plus to minus. So we're going to write a KVL expression going around that loop right there by saying then that negative V sig, so minus to plus is a negative V sig, dropping down here plus VGS, plus the voltage drop across this resistor, which is just the current G sub M VGS times R sub S, or the voltage drop across that resistor then is G sub M times VGS times R sub S, and the sum of those terms equals 0. Now, if we rearrange this expression here, adding V sig to both sides, and then factoring out the VGS from both of these terms, we get then that VGS times 1 plus G sub M R sub S is equal to V sig. Solving for VGS, we get then VGS is equal to V sig divided by 1 plus G sub M times R sub S. Now with this expression of VGS, and you'll notice that it's the same expression that we got over here using the voltage divider, we can then plug this VGS into this expression, and we get the same output voltage expression. V out then is equal to negative G sub M times VGS, which is this term right here, times R sub D in parallel with R sub L, which is that expression right there. And once again, there's no reason to take the time to do it, but we can calculate the total gain. The total gain, whether we use the hybrid pi model or the T model, is going to be exactly the same. It's this negative G sub M times 1 plus G sub M R negative G sub m times 1 over 1 plus G sub m R sub s times R sub d in parallel with R sub L. Which, if we plug in the values that we have for this circuit, we have negative G sub m, well, G sub m is 1, so it'll be a negative 1 milliamp times 1 over 1 plus 1 times, now R sub s is 6 kiloohms, times R sub d in parallel with R sub L, that's 6 times 10, or times 6 times 10 divided by 16, and that turns out to equal a negative 0.54 volts per volt. You'll notice the effect of R sub s. If R sub s was 0, this term right here would be 1. But R sub s not being 0 makes this term here a value less than 1 and reduces the overall gain by that factor 1 over 1 plus G sub m times R sub s.